Hey Data Junkies, welcome back. We're starting a whole new module on analysis of variance, or ANOVA for short. I'm very excited to be starting this module with you here as we're taking our next steps as we work towards regression analysis, and we've got a lot of great topics to talk to in this particular module here. So let's go ahead and get started with the first introductory topic on one-way ANOVA, where we're going to talk about what is a one-way ANOVA or analysis of variance, introduce the concepts of an F ratio and the F distribution and things like that. So the foundations video, this is the first video we're going to start up on, is going to be followed with some how to do these by hand, post hoc testing, Welsh analysis, and a whole bunch of other great tools here. But let's go start at some very basic fundamentals and see what are the sorts of research questions you could ask with a one-way ANOVA. So the questions here I'm posing are the sorts of ones we could use with the General Social Survey data, the GSS. All of these are variables that have been taken from that particular data set, but could be used with a one-way ANOVA to answer them. So these sorts of questions could be things like, how do Protestants, Catholics, and Jews, and atheists vary in support for capital punishment? How do Republicans, Democrats, and Independents vary in terms of their income? Or how do older, middle-aged, and younger people vary in terms of their frequency of church attendance? What do all of these things have in common? Well, for starters, they're all asking something that has some sort of numerical dependent variable, something that can be quantified and counted. And the independent variable is something that is categorical. These are groups of religion, groups of political identity, groups of age. And the dependent variable were things like varying in support of capital punishment. That's a bit more of an ordinal measure, but when you address it out to a Likert scale or something that has these longer ordinal strands, they can be treated as if they're numeric. Income is something that can be measured numerically. Frequency of church attendance, it's right there, frequency in its name, so that's something that gets counted. Now, taking another step back here, I mentioned earlier that analysis of variance is what the full name, and it's ANOVA for short, and it's similar to t-tests. We just covered t-tests not long before coming to this, and the t-tests were dealing with a very similar situation where you had a numeric dependent variable and a categorical independent variable, but you could only compare two groups with the t-test at the most, whereas the ANOVA does three or more. You can technically do two groups with an ANOVA, but then you're just doing an overpowered t-test at that point. So really we're using this for three or more groups, and because we are dealing with means of numeric dependent variables, this is a parametric inference. So this is part of the parametric testing. We'll be talking about some non-parametric alternatives to this a little bit later. Now, one of the big things that we're talking about with ANOVA, it's in the name itself, analysis of variance, is now we're talking about this concept of variation inside of our variables to be measured here, but we're talking about variation that is within and between. We now have two types of variation, where before we were generally talking about one. So what do I mean by this within and between variation? Well, on the screen I have where you on the side you see this sort of color shifted bar that goes from yellows, reds, blues, and greens. And we can say that this would be the representative of some category that says there are four groups here, and each group is a particular color group: red group, yellow group, green group, and blue group. Next to that is a vector of numbers, some sort of count data that we'd be working with here. And this is how it might appear in some sort of CSV or other flat file where it's a sort of spreadsheet view, where in one column you have the variable of your groups and the other one you have a variable of the numerical measure. We can extrapolate that out to where I have it on the center of the screen, and then take each of the colored groups and group them all together so that everybody on the red is together, everybody with yellow is together, everybody with green is together, and blue is together. And so we can think of this as having four separate columns of data, where each column represents a categorical group, and the values inside that column are the numeric measure as well. Now let's take that instance here where we have them broken out into their groups, and let's talk about the two different types of variation. Variation within a group is saying, if I was to look at, say, the blue group, everybody inside the blue group is going to have some sort of numerical answer to whatever it is that we happen to be measuring here. And everybody's going to have a slightly different answer. So that's going to mean that there's going to be some variability within my particular group, and that's the variation within the group. Now, each of the groups are not going to be identical to each other. There's also going to be some differentiation between those as well, and that's where we're getting the variation between the groups. Blue group is not going to look the same as the green group, the yellow group, or the red group, and others vice versa. Now, when we're dealing with these two types of variance, the analysis of variance, the ANOVA here, is looking and really focusing on these two different types of variation. If we were to take the spreadsheet sort of view that I just mentioned and put it more out into sort of a distribution graphically, what you might see are different curves, one curve for each group, and the center of those curves is going to be a mean. And what we're looking at then is the distance between these particular curves. That's your between group variation. How far apart are these groups from each other? And the within group, that's referring to how spread out is it? How much variation does that one particular curve have? Is it tall and skinny? Is it short and wide? Does it overlap well with the others? So these two types of variation are going to be playing off of each other when we're taking these looks. Now the basic logic, as I mentioned before, with the study design of a one-way ANOVA, is that we have an independent variable that has minimum of two categories. Really, it's three or more. And we have a numeric variable, which is interval or ratio. I also said that you can get away with using an ordinal variable if it has 5 or more ordinal categories. And what we're really honing in on this is to see, are there differences between the sample means of these different groups that are so large that we can conclude that the populations represented by these sample groups are indeed different, right? Each of the groups that we're looking at is a sample from its respective population, and we're comparing these samples by their means to see if they're different. It's an extension of the t-test, okay? Now the basic logic when we're dealing with this going into hypotheses here, the null hypothesis for a one-way ANOVA says that there's no difference in the population means. They're all going to be equal. Doesn't matter which groups they are, they're all going to be equal. The alternative takes a slightly different track. It says that at least one difference is in the population. One of them is different. We don't know which one. Sometimes we care, sometimes we don't. But really what we're saying is one of them is different. We're not exactly sure which one when we set up the alternative, but as long as one of them is, then we can reject the null. And we write it out symbolically that the mu of group 1 is equal to the mu of group 2, is equal to the mu of group 3, and so on, all the way through group K, where group K is the highest or most number of groups that you have. And the alternative says essentially the same thing, but instead of making them equal, we're making them listed as not equal. Now keep in mind when you're writing this in symbol form, this is not saying that all of them are not equal to each other. What we're saying is at least one of them is not equal. And because these could be nominal groups as well, the ordering of them in which they appear doesn't necessarily always matter. So if you're dealing with some sort of ordinal category, there may be a natural ordering and ranking if you say as one is more or less than another, but in nominals these just could be completely mixed up. Now if we're saying that the null is true, what we're saying then is the sample means should all be about the same value. And if it's false, there should be substantial differences between the categories, combined with relatively little difference within the categories. Let's take a closer look and see what this means and how this can play out for our hypotheses. Now when we said that the differences are larger between the samples, this is going to be more likely that the null is false, especially when there's a little difference within these categories. We're going to reject the null, saying that there's difference between the populations represented by their samples. So what we're dealing with here is this variation of within and between. It's a ratio. The variation within is in the denominator, variation between is in the numerator. Now because this is a ratio, the lower number gets divided into the upper number, and we have some value. If they're relatively equivalent to each other, they'll be close to 1. And if the denominator, as it gets larger, it will make your number lower than 1, closer towards 0. And as the numerator is larger, that's going to make your number much larger than 1. And that's where we're dealing with this ratio. So you can keep in mind then, as we get changes between the withins and betweens, it's going to affect how our variance ratio turns out. So if you have little and decreasing variation between your groups, that's going to shrink your numerator. It is just as well if you have an increasing amount within groups, then that's going to increase your denominator, and it's going to cause for a smaller ratio. That means that you're going to be less likely to be statistically significant because your ratio is going to be smaller, and it's going to be less likely to mean that your means are different from each other. Conversely, if you have increasing variation between, that means you're getting a larger numerator. If you're having decreasing variation within, or small amounts of variation within, then you have a smaller denominator. Both of these contribute to having a larger ratio value. When you have a larger ratio value, that means you're going to be more likely to be statistically significant that at least one of the means are going to be different. Let's see this graphically here. So when we're visualizing this out graphically, the differences that we're starting to pick up, that when you have small variation between your groups, then you're going to have a substantial amount of overlap between your different distributions. They're going to be harder to pick apart, harder to say that one is different from the other. And as the variation between groups rises, this could be between all of the groups, or it could just even be one of the groups. We're not really sure, picking on any one in particular at the moment. But just generically speaking, that as your variation between increases, the distributions move farther apart from each other. They become easier to see relative to each other, and then say that yes, they are indeed different enough from each other. And so if I was to go ahead and say that we go to the largest, they are indeed the farthest apart relative to the others. If we're talking about variation within the groups, this follows that same sort of logic, but instead of the distributions moving, if you can think of a left and right sort of manner, away from each other, when we're talking about variation within, if they were to all have the same mean, they would all be stacked on top of each other. And then what could change is their standard deviations. So as we are changing the shapes of their standard deviations, they are blowing out and becoming wider, or they're sucking in and becoming taller and narrower. And so the more overlap there is there, then the more alike they are. So when your variation within shrinks, then they seem to be more similar to each other. There's less variation between them. Keep in mind, this is in the denominator. So as your variation within shrinks, there's less differences within each of these groups. They're more alike. So it'll help illuminate the differences between the groups, right? And that's what we start to see when the variations are small. Now the advantage to the ANOVA is that it saves time and energy over doing a bunch of t-tests. If you had to do t-tests, you'd have to do one t-test for every pair that you had. Let's just take three groups, A, B, and C. If you had A, B, and C, then you'd have to do a t-test for AB, BC, and AB. So immediately you'd have three tests you'd have to run instead of one. And you already have an advantage with the ANOVA there. The second advantage is much more of a critical one, and that's because it's going to affect your type 1 error rate, which I'll go into shortly. When we're dealing with the type 1 error issue, this is what we call an alpha inflation. When you're doing a t-test or some other comparisons of means test, you set a particular alpha level and say, that's the most amount of risk that I want to take. Typically we use alpha at 0.05, so that's what I'm going to use for this example here. And so you say, I'm going to be confident at 95% that the difference between two groups, in this case we'll say A and B, that my alpha is 5% or 0.05. And that's flat. But there's something mathematical that starts to happen, that when I start to do these tests, the first time I do a test, we'll say between A and B, I have an alpha of 0.05 or 5%. When I do another group between B and C, then that's another alpha of 5%. And then when I do another one between A and C, that's another 5%. And these are not independent of each other. I could potentially commit a type 1 error the first time, maybe not, 5% risk. The second time I might commit a type 1 error, maybe not, 5% risk, and so on for every pair that I have. And this actually has an exponential compounding effect. We can see it mathematically as your true alpha being 1 minus 0.95 to the power of n, where n is the number of pairwise tests that you need to commit. So if I actually had to do 3 tests with groups A, B, and C, then that would be 1 minus 0.95 to the third power, which comes out to about 0.143. So there's going to be actually, instead of a 5% alpha, about a 14.3% alpha there, that I might, just by doing 3 different tests, have increased the chance of committing a type 1 error on at least one of them is up to 14.3%. And this is what I call an alpha inflation, and we can help control for some of this by doing an ANOVA, and it saves us a lot of precious statistical resources there. Now, these particular graphics come from the online stat book online. It's a great website. I highly recommend you check it out. And what they show here are a couple of different exponential curves. The first one is talking about how much, as your pairwise tests increase, how does this happen to affect the number of means that you're going to be having to compare? And the second one is talking about the probability of committing a type 1 error based on those number of means that you have to compare there. So the first one's talking about pairwise tests based on the number of means. So the more groups you have, the more pairwise tests you're going to need to do exponentially. And the more pairwise tests you need to commit, the more type 1 error you're going to be inflating. So these go hand in hand with each other. Now, the other side of the ANOVA here is what I call a low bar test. And low bar could also be described as a low threshold. And what this means is, think back to our alternative hypothesis. The alternative hypothesis said that only one mean had to be statistically different from the rest. So because only one mean has to be statistically different from the rest, then as long as, when we're doing these pairwise tests, as long as one of those differences pops as statistically significant, it's going to raise a flag, and the entire ANOVA analysis is also going to be statistically significant. Not such a big deal when you have, say, only 3 groups and you're comparing them. But imagine if you had 5 or 10 or 50 groups and all of the different pairwise tests you're going to be doing. And all you need is at least one of them to pop statistically significant, and it's going to trigger the entire ANOVA. Now, we do have some controls on there when we do the post hocs, which we're going to get to, and then talks about how it controls for its p-values, or the degrees of freedom that are going to come into play when you're talking about your F distribution. Some of these are going to have some controls to go into place. But really, the more pairwise tests you have, the more chance you're going to have at least one to be statistically significant. And that's the point I want to try and get across here. So we, of course, with all of our parametric tests, we have a broad array of assumptions that need to come down here. Some of these are a bit more heavy-hitting than others. The first one, of course, we mentioned that your dependent variable is numeric, interval or ratio. It shouldn't have any extreme outliers. We'll talk about how to take care of that in a second. Normality. Now, normally we're talking about a normally distributed variable, your dependent variable. And you can usually use that as a decent eyeballing here, but what we're really talking about is normality of the residuals. We'll talk about those in a moment here. The next one is homogeny of variance, which is a fancy way of saying that the variation and the dispersion of your different groups are relatively similar to each other. You should have independence of observations, so one observation should not be unduly influencing another one, and you should hopefully have things like random selection in your sampling method to help make sure that you have the best equal probability selection methods and random data. So the last couple more we have are that your group sample sizes should be approximately equal. In reality, this doesn't always happen, particularly if you're doing more of an observational study that's not in a controlled setting. But as long as your samples are indeed relatively equal, this is going to build in a bit of protection for you when you're doing your ANOVA. We call this robustness, and it's going to protect you against differences you might have in normality and variance, which we'll talk about shortly. And once we have this ANOVA put together, if we start to have compromises on some of these assumptions, we do have some alternatives that we can reach out to. So looking under the hood at the math machine, this may look a little frightening to you at first. This is the F statistic for the ANOVA, and there's a lot going on here. There's a lot of moving parts. But what we can do is actually take it off in bite-sized chunks and pieces to get this thing calculated. Now, the elements that go into the formula, there's N, which is your sample size. K is representative of groups. I recognizes for an individual, whether it's a person or an object or whatever it is you're measuring. X is a particular observation, where an X bar is a mean of those observations. X bar sub K would mean the mean of a particular group, and so on. We have a few different degrees of freedom. I have 3 of them listed on here, but you only really need 2 as we're looking at. The DFSST is short for degrees of freedom for sums of total squares, or total sums of squares. That's talking about the degrees of freedom for the entire F test here. And that's represented by K times N minus 1. Degrees of freedom for the sum of squares between, and that is represented by K minus 1. It's also in the denominator part up in the numerator. Yes, this is a multi-level division problem here. And we also have the degrees of freedom of the within, which is represented by N minus K, or also N minus 1 times K. Gives you the same answer. And let's go ahead and take a little bit, break this apart, make it seem a little less frightening for you here. If we look a little bit closely, we can see there's a giant part of the numerator, a giant part of the denominator. The numerator is what we're going to call, it's going to calculate out the sums of squares between and its degree of freedom. Those two are going to divide to give us the mean sums of squares between. And then the denominator, that's going to give us the sum of squares within. which is going to be divided by its degree of freedom to give us the mean sums of squares within. Now, the within is representative of what we call the residual or the error, the stuff that's left over that we don't quite know how to predict and explain. And the between is what we can see, the strength of the evidence. Now, when you get the strength of the evidence and you divide it by an unknown amount of error, that's how we get the F ratio, the between over the within, and that generates F. Breaking out the math machine here, I just have a slide to kind of help show you a few more bits and pieces of this, but we're going to revisit this slide as we go and work our way through here. And I just want to talk a little bit about the F distribution. This is a new one to add to your lists here. The F ratio, we said before, it's a ratio statistic between the mean sums of squares between and within. It has 2 degrees of freedom, the degree of freedom between, the degree of freedom within. And previous hypothesis tests that we're dealing with, t-tests and chi-squares, they only had 1 degree of freedom. The F-test has 2, and the relationship between those 2 degrees of freedom is going to dictate the shape of the F distribution, whether it's hugged very tightly to the left or if it's starting to move out towards the right and bubbling outward. And as those degrees of freedom increase, the skew of the distribution decreases. It starts to bubble out more. And it's non-negative, so the left tail is bound at 0. There are no negative F statistics. Keep in mind these are ratios. And it just goes out to infinity onto the right. And just like think of it when we had the chi-square tests, that you had a chi-square critical value that was also bound to a non-negative distribution. And so long as your statistic was larger than that critical value, you were statistically significant. The same thing's going to apply here with the F distribution, the F ratio. So you're going to get an F critical value based on your alpha and degrees of freedom. And from there, you're going to see if the F statistic you obtained is larger than your F critical value, and then you can determine if you're statistically significant or not. Now, I touched on before that because F was a ratio, if the two are relatively equal to each other, it's going to come out to be about 1, the F ratio itself. And so if there's really no difference between these particular groups by their means, and we can kick in the central limit theorem to help us prove these particular things, then the ratio is going to be closer to 1, or less than 1, meaning there's going to be less differences, but closer to 1 more specifically. And the alternative is going to say something else. It's going to say the larger we are from 1, the larger the difference is, the smaller the withins, and the more difference we can say exists between the different groups here. So much so that it would be able to reject the null hypothesis that we have this sufficient amount of evidence. Now, when we're reporting the F statistic, we're using APA citation in this course, and it breaks out by starting with the letter F, open a parenthesis. Then you have 2 numbers. The first one is your degree of freedom between. The second one is your degree of freedom within. Close your parentheses, equal sign. Then you put in the F ratio that you obtained, comma, and then you put in your p-value. Now, keep in mind, when you're dealing with your p-values, I have to tell you again, that do not put in a p-value with scientific notation. Round it to 2 decimals or add in additional leading decimals until you get to your first non-zero number. Now, if you're reporting an exact p-value. If you have a very small p-value, you're more than welcome to just say p is less than your alpha. Or if you want, use a smaller number than your alpha to show that it was even more statistically significant than the alpha you had previously set. Conversely, if you're larger than your alpha, flip that inequality around to say that p is greater than your alpha. And so either way, p is less than alpha or p is greater than alpha is completely acceptable and widely used. And the ANOVA comes in many different flavors. In this course, we're only going to be talking about the one-way ANOVA, but there are other different types that you may want to learn about after this course or depending on where you go with your career trajectory. And I'm just going to mention some of them here so you get to, because you may hear about them on the internet and as you're doing your research. And I don't want you to get confused with how they pertain to the one-way ANOVA in case you think that, you don't want to confuse the two when you're getting your work done. So the one-way ANOVA, it's also called a between subjects ANOVA. This is your one numeric DV with 3 independent groups. Now we have what's called a one-way repeated measures ANOVA. The repeated measures is the introduction there. It's also known as a within subjects ANOVA. This is just like the one we're working on now, but it's designed for paired testing. Think of the pre and post, things that happen over time, etc. Now, factorial ANOVAs are just like one-way ANOVAs, except we can add in additional independent variables that are typically categorical. And so you've got 2 or more categorical independent variables. And we can see how they play off of each other and interact with each other as they pertain to the dependent variable. Mixed ANOVAs, also known as within-between subjects or SPANOVAs, these take 3 or more independent groups just like our one-way, but they also take them over time periods. So it's taking the one-way and it's combining the paired effects of the one-way repeated, and it's mixing them up into a mixed ANOVA. The next one is what we have is called an ANCOVA. So we go from ANOVA to ANCOVA, and this is where we're taking one numeric DV. Then we have 3 or more independent groups, so far we're looking like the one-way ANOVA. But then we add in more more numeric variables along with our categorical. So you have at least one categorical and at least one numeric, and then they can mix off of each other. So ANCOVA is short for analysis of covariance, where the covariance comes from the fact that you're adding in numerical independent variables. MANOVA is short for any ANOVA model that puts in more than 2 dependent variables. So you have more dependent variables here. The first one of the ANOVAs that does this. In fact, MANOVA is short for multivariate ANOVA. And the last one is MANCOVA, which is short for multivariate ANCOVA. So it's any MANOVA variable with at least one categorical IV and one numeric IV. And so it's sort of taking flavors from a lot of what came before it. And so this is sort of the family tree of the ANOVAs. Just wanted to give you the sort of brief introduction. You do not have to remember these in any way. Just wanted to give you a passing familiarity to it. And with that note, I'm going to cut this particular video here. I'll see you in the next one where we actually solve ANOVA by hand. See you next time.